Next, we will discuss about the internal architecture of 8086 microprocessor. The internal architecture of 8086 microprocessor consists of two functional units, namely BIU, that is bus interface unit, and EU, that is execution unit. We will see the diagrammatic representation of 8086 architecture. So, this is the 8086 internal architecture. It consists of two functional units, BIU. BIU refers to bus interface unit and EU refers to execution unit. The function of this BIU, that is bus interface unit, the function of this BIU bus interface unit is to establish communication between the 8086 microprocessor and the function of this BIU is to establish communication between the 8086 microprocessor and the corresponding IO or external devices. It consists of an adder that is used to convert the logical address into physical address, which we will be discussing about. So, this adder is responsible for converting logical address into physical address. This logical address is of the form segment address is to offset address. So, these segment address and offset addresses are obtained from four types of segments: ES, CS, SS, DS, that is extra segment, code segment, stack segment and data segment, and we have discussed about these segment registers in the last session. And the last logical component is IP, that refers to instruction pointer, which contains the offset within the code segment. So, these are all the main registers present in this BIU, that is bus interface unit. And the next logical component of this bus interface unit is the instruction stream byte queue, which is of 6 bytes long. So, this is a pre-decoded instruction byte queue. Pre-decoded in the sense when your processor, that is this execution unit, is executing any instruction, when this EIU, that is execution unit, is executing any instruction, this instruction stream byte queue will prefetch the next instruction to be executed and put it in the and arranges it in the 6 byte queue. The next logical component of this BIU is the instruction stream byte queue, which is of 6 bytes long, and this queue is responsible for prefetching the opcode bytes for the next instruction to be executed by this 8086 microprocessor. Next comes the logical components of execution unit. So, this part refers to the execution unit of 8086 microprocessor, and it contains the arithmetic logical unit, ALU. This is responsible for performing various arithmetic and logical operations such as addition, subtraction, increment, decrement, AND, OR, XOR, etc. And it consists of general data registers AX, BX, CX, DX. That is, AX is accumulator, BX refers to the base register, CX refers to the counter register, and DX refers to the data registers, and we have discussed about each of these functions in the last session itself. And each of these registers are divided into higher order registers such as AH, AL, BH, BL, CH, CL and DH, DL. So, the letter H refers to higher order register and L refers to the lower order register part. Combinedly, we call it as AX, BX, CX and TX. This SP refers to stack pointer register, BP refers to base pointer register, SI refers to source index register, and DI refers to destination index registers. All these registers are used to contain the offset address values. For example, this SP contains the offset within the stack segment and BP contains the offset within the base register, and SI refers to and the SI contains the offset of the source data and DI contains the offset of the destination data. So these registers are used for storing various offset values. And next part contains the operands and the flags. So these are required by arithmetic logical unit for performing the operands. So these operands and flags are required by arithmetic logical units for performing various operations, and the flags are used to indicate the status and the control of the 8086 microprocessor. Since we have already discussed that flags are classified into two categories as status flags and control flags. The 6 types of status flags are auxiliary carry flag, parity flag, sign flag, zero flag and overflow flag. And the 3 types of control flags are trap flag, interrupt flag and direction flag. So these are all the logical components present in the execution unit, and the last part of this execution unit is the control system. So this control system is made up of a decoder and timing and control unit. So the decoder is responsible for decoding the opcode bytes for the instructions or data that are obtained from the instruction byte queue. And for the decoded opcode bytes, the timing and control units will generate the necessary control signals in order to execute the corresponding instruction. So these are all the functions of the 2 units, bus interface units and execution unit. So this is all about 8086 internal architecture. Next, we will discuss about the concept of memory segmentation. We already know that the total memory capacity of 8086 microprocessor is 1 megabyte. So this 1 megabyte of memory size is divided into segments. So this process of dividing memory in such a way, that is into segments, is called as segmentation. So the purpose of segmentation is that increase the execution speed of the processor. Now let us discuss deeply about the segmentation process. Data will be stored in memory in the form of bytes, and each byte will be allocated with the memory address. We know that in 8086 microprocessor, the address bus is made up of 20 bits. So the total memory capacity that can be addressed by 8086 microprocessor is 2 to the power of 20, that is approximately is equal to 1 megabyte. So this 1 megabyte of memory is further divided into 16 logical segments. And the size of each segment is of 64 kilobytes, and each segment consists of a logical address which is of the format segment address is to offset address. Example, the segment address ranges from the value 0000H to F000H, and the offset address ranges from the value 0000H to FFFFH. Now let us discuss about the diagrammatic concepts of this memory segmentation. Now let us discuss about the diagrammatic concept of this memory segmentation process. Consider this as the total memory size and is divided into 16 logical segments, and this is the example for segmentation, and this is the example for segmented memory, and each segment consists of the segment address and offset address. For example, when you consider this physical memory location 4000H, and it is abstract, and this can be abstractly viewed as segment address is to offset address. So, the segment address refers to the base address of any segment, and this offset address refers to the displacement value from the base admins to the memory location where the actual data is residing. So, that is called as displacement value. Suppose if the data that's required by the processor is residing at the memory location 0250, then this is the displacement value, and we can take the logical address as 4000 is to 0250. Here this 400 refers to the segment address and the 250 refers to offset address. So, the processor can directly go to the location 4000 and to the offset address value 0250 and fetch the data easier and faster. So, this is the purpose of memory segmentation. Now, let us discuss how this logical address is converted to the physical address, which is of 5 bits. Here, each of these segment address and offset address are made up of 16 bits, but the physical address value is made up of 20 bits. Now, let us discuss how the 16 bits are converted to 20 bits. So, the segment address, that is of 16 bits, and offset address of 16 bits is given as input to the adder that is located in BIU, that is bus interface unit, and this adder will convert this logical address into physical address, which is of 20 bits. Now, let us discuss about an example for conversion process of logical address into physical address. Suppose the given segment address is 400H and the offset address is 0250H. It will be converted into physical address by adding 4 bits to the left of the segment address. So, this is the example of segment address 4000H and example of offset address is 0250H. So, this combined logical address will be converted to physical address by shifting 4 bits. So, this combined logical address will be converted to physical address by shifting 4 0 bits to the left of the segment address. The binary representation for the segment address is 0100 0000000000. Now, in order to convert to physical address, we will be shifting 0 bits 4 times to the left of segment address. After shifting 4 bits, now add the corresponding offset address with the segment address value. The offset address value is 02500H. Now add it with the segment address. If you add that 0000 and 0010, 0101 and 0000. If you add this, you get the value 0000, 1010, 0100, 0000, 0010. So, the corresponding physical address will be 40250H. So, this is the corresponding physical address for the given logical address 4000 is to 0250. So this is how the conversion takes place. That is 16 bits of the segment address and the 16 bits of offset address are converted to physical address which is of 20 bits. So this is all about memory segmentation process.